So, good morning. Dear guests, dear speakers, dear support team, welcome at our annual and final DigiMed Bayern Symposium. We, the consortium, want to make sure you have a pleasurable and fruitful day. And for that, our physical hosting here is of relevance, of course. And dear Dr. Zies, thank you very much for hosting us today. And it's a great honor that you, as the medical director of the TUM University Clinics, open our conference. And with that, please come on stage.
Yeah, good morning, everyone. Dear ladies and gentlemen, it's a great pleasure for me to welcome you all. On behalf of the management team of our TUM University Hospital, I would like to thank you very much for joining us here at the Translatum in Munich for the DigiMed Conference 2024. I really hope that you will enjoy this meeting on big data from patients and that you will find it as exciting as it actually is. Today, we stand at a critical juncture in healthcare. The explosion of digital technologies enables an unprecedented collection of data from patients, ranging from electronic health records and genomic sequences to wearable health devices and patient-reported outcomes. This wealth of information offers us unique opportunities for the prevention of human health and the treatment of diseases. Big data allows us to identify patterns and trends that were previously hidden. By analyzing vast datasets, we can better understand the epidemiology of diseases, uncover risk factors, and identify potential health disparities. This knowledge is crucial for developing targeted prevention strategies, ensuring that our efforts reach those who need this most. Moreover, big data facilitates personalized medicine. Every patient is unique, and their responses to treatment can vary significantly. By harnessing data from diverse patient populations, we can tailor therapies to individual needs, ultimately leading to more effective and efficient care. Imagine a future where treatment plans are not just based on generalized guidelines, but are specifically designed for each patient, informed by their unique data profile. However, the journey to harnessing patient data is not without challenges. Issues of privacy, security, and ethical use are extremely relevant. As we analyze and utilize this information, we must ensure that we respect patient autonomy and maintain trust. In addition to these considerations, collaboration is key. The complexity of healthcare data requires interdisciplinary approaches, bringing together experts from various fields: data science, medicine, public health, and ethics. Today, I encourage you to engage with one another, share your insights, and explore opportunities for collaboration. The breakthroughs we seek will only be realized through shared knowledge and concerted efforts. As we are at the beginning of our conference today, I invite you to keep in mind the ultimate goal of our work: improving health outcomes for patients. Whether through innovative research, new technologies, or enhanced clinical practices, our mission remains clear. We are here to drive forward the understanding of diseases, empower patients, and to push forward groundbreaking advancements in prevention and treatment. In closing, I want to express my gratitude to all the members of the DigiMed Bayern and Harry Schunkert for your commitment to this great work. Your expertise and passion are the driving forces behind this project and the potential we see in big data. Together, let's embrace the opportunity to shape the future of healthcare and improve the lives of countless individuals. Thank you very much for your attention and have a great day here at the Translatum.
Thank you very much, Dr. Zies. Do we have a switch here for the screen? here it is. Got it. Nothing happens? Ah, okay. Ah, yes, okay. Now it doesn't work anymore. Zurück geht nicht, ne?
Der da. Ach, nicht der.
Ah, okay, der ist das. Alles klar. Okay. Und wie geht's nach vorne? Ah, okay, alles klar. Dankeschön. Dankeschön. Okay. Dear guests, the sponsor of DigiMed Bayern, the Bavarian Health Ministry, has invested a total of over 24 million euro from the taxpayer to the idea to pioneer new big data supported medical concepts framed by the expression P4 medicine. After 6 years now, our pilot project ends of the 30th of this month. We have committed to hold an annual public symposium to showcase what has been achieved and for scientific and medical reflection. Today is our final show, and we appreciate your interest and your contributions. Can we find out now if such an investment pays back to the citizens? The cost side of such a project is under good control. Half of the investment goes into staff. The third, for other operating costs, goes largely into molecular measurements with high throughput technologies, again with staff contributions. So staff and people are everything. And here they are. Some colleagues from that kickoff team are still with the project. Many are here in the room, and some will present today. Coming back to the return on invest, please allow me a standard business case consideration. In industry, we would simply measure the sales, sum it with the costs, and where the resulting line here in blue hits the zero, we are profitable. There's a sum under the curve. If it gets positive, we made our return on invest, and we are continuing so. Of course, such a consideration does not so much apply for a project like DigiMed Bayern, but I still find it very useful. So how could we measure the return? A measurable thing is the number of publications achieved by the project. But still, now we have something quantitative, but still we don't know which contribution came through the particular funding, and we cannot easily assess the quality and the impact of the outcome. So in the conclusion, I think we should still try to measure the return of invest and try to report it in the best way. But a second finding is, and I will come back to this, is that the return of investment grows with the availability of fair data and the data use and the value which has been generated with this. And with fair, I mean the action sense: found, assessed, interoperated, and reused. In a nutshell, what have our work packages gained? A data integration center has been built at the German Heart Center Munich, delivering access to hundreds of thousands of patients partially involved in clinical studies. This data integration center is fully operative and partially serves as a blueprint for others. These data have been largely enriched, mostly with high throughput molecular analysis. The data set has been complemented with epidemiological cohorts. Biomedical conclusions have been drawn from all that. The Veroni study focuses on a particular genetic disease and implemented medical follow-up. Up to 30,000 children have been screened. Finally, the expertise, findings, and infrastructure made a good step forward to the medical prevention in Germany, with the Gesunde Herzgesetz, healthy heart legislation approved this year by the federal cabinet. Our HerzFit app for cardiovascular prevention has reached almost 150,000 downloads. This is roughly in the range of the last year's subscription of digital health application DiGAs across all Germany, but each DiGA subscription is only for 3 months, and the total costs of this have been 75 million euro. I think this should kick off some discussions about this concept. Health insurance data sets have been of several million patients have been made available and are under analysis. We have intensively aligned our processes with the Bavarian data protection authorities. But with all this, we should also be transparent with what is the hardest nut still to crack, and this is to create an exemplary and transferable integrated digital infrastructure. In 2018, it was clear when we started the project that we need a collaborative, trusted research environment, but nothing was available. So we decided to build our own private cloud, both as a blueprint and for our own use. For that, we identified and onboarded the Leibniz Supercomputing Center. We launched our DigiMed cloud 1 year ago, but with major delays due to several difficulties. Finally, the overall DigiMed team made valuable big data available and used them successfully. Data will be generated to the last minute of the project. But even now at the project end, there's still no trusted research environment as a service available. If we don't care, the value of the data will get lost and will not be used to the full extent. Moreover, we are just making visible a problem which is much bigger and also other projects and institutions experience, and which has a considerable negative impact on the return of invest. Finally, such a required trusted research environment should be a standard service. It's an infrastructure, not a project. It's like streets and buildings. But let's come back to what is actionable, go away from complaining, and what we can do ourselves. We want to continue the operation of our trusted research environment and extend it towards what we call DigiMed Bayern Secure Cloud 2.0. That would allow continuous collaborative data access and exploration. Latest at the end of 2027, our resources should migrate into what we are finally aiming for, the Bavarian Cloud for Health Research. Our team is able and willing to support the BCHR and contribute building blocks. But how do we achieve on this way a critical mass and scaling effects, realize scaling effects? The DigiMed Secure Cloud serves as a technical basis for the future Bavarian Genome Computing Center, finally operated by TUM Klinikum. This operation is part of the National Modellvorhaben Genomsequenzierung, aiming to improve care for cancer and rare diseases, in a fruitful interplay with research. In our cooperation, DigiMed 2.0 will benefit from the expertise and resources the other side has available, particularly with medical genomics, with processes, with interoperability, data standards, and international connectivity. Per default, ownership and data access are strictly separated. But together with one physical cloud, or TRE, infrastructure at the LRZ, we get critical mass. End of next year, we could have like 12 petabyte of secure storage in operation. And other projects like Bavarian Genomes for rare diseases are eager to join with own resources. The conclusions. The assumption that you can generate big data with big money and health with data support seems to work. And all of what has been achieved is already part of exciting follow-up activities with additional third-party funding. The weakest link in the chain, or other way around, the biggest potential, is in a trusted research environment as a service. Last but not least, the above formula is, of course, a reduced view. There's enormous value in such health data which can and should be leveraged, finally, also with ethical financial contributions, I think. And health is also worth money. And in the political reality, health, science, and economy are separated buckets or silo-like. But if we think and act in synchronization, there's a lot to win with data-driven and generating approaches in medicine from all perspectives. Let me finish with a big thank you to our sponsor, the involved patients, and with compliments to wonderful colleagues for their drive, for their achievements, and for a good time together. Thank you very much. And now we switch to the scientific and medical part with Professor Heribert Schunkert, who's heading the cardiology department of the German Heart Center. And the stage is yours.
Thank you so much also for sharing this session, but also sharing the whole endeavor of DigiMed Bayern. It was not an easy task, really, to bring everybody together, from the ministry to all the managing agencies, to the researchers and all those who do work at the bench or in big data sets. So thank you for the management. Also, I want to start with my special thanks to Professor Domdai, who actually created the idea of DigiMed and approached me with the concept that I tried to fill with scientific contact. So what we wanted to do is to fight atherosclerosis with personalized, preventive, predictive, and participatory medicine. This is being done very actively in the field of oncology, but much less so in the field of atherosclerosis, which is the biggest killer, nevertheless, in Germany and the entire world. And we wanted to build a second stepping stone in this 4P medicine. So the concept is to generate data from individuals, from groups, and to make these accessible for better care of individual patients. This seems to be very simple, but indeed it's a bit challenging. But to make that digestible, we wanted to develop applications and transferable infrastructure to improve patient care in coronary artery disease and stroke. So this is the more concise concept that we wanted to go for. And you have heard already a bit on the infrastructure that we generated in this respect. This is a collaborative endeavor, and these are the institutions that are involved. Many thanks to all who made that possible across the boards. And in my resume, I think the first conclusion is that it was a highly productive collaboration crossing borders. Borders in sense that there were very heterogeneous institutions involved, very heterogeneous concepts, but nevertheless we worked together and we crossed these borders from medicine to basic science, from computing to ethics, from big data to a legal framework that is necessary really to make a work like DigiMed Bayern happen. So this was a core concept, and I want to start with the data safety, ethical and legal issues, because without these, it's not really possible to transfer the idea of DigiMed and other concepts into society. So for this, I'm very thankful for the collaboration that we had with the Institute of Theology, Technology and Natural Sciences at the LMU, where we developed ethical concepts really to understand the framework in which we are working in and to make this work happen. So ethical consent, individual consent, legal consent, and societal consent are very important concepts. They are not that obvious for basic researchers or clinical researchers because we all have our concepts on ethics, but nevertheless we have to bring that into society, and for this it was important for me to learn from all these institutions, and I'm very thankful that these ideas really were brought in the concept of DigiMed by Professor Domdai. So I mean, with this in in the background, we wanted to create big data that cross borders also in the silos that we have in clinics. There are different databases from imaging to laboratory data to clinical data and to research data. And to bring all this together, we had to develop a concept, and this was a major effort over the last years to build this trust center where we can really bring together all different kinds of quality of data into a big database, a data lake that allows analysis across borders for individual patients and long-term follow-up. And the next step, of course, is to make that accessible to a wider community. And for this, this needs to go into the internet, but in a way that it's accessible based on the legal and ethical standards that we should have in our society. So the Health Cloud is what we wanted to create, and with this we joined up with the LRZ, which was a difficult communication, to be frankly in this aspect, because the languages that we speak in clinics and in research and the language that is being spoken in a supercomputer hosting agency is very different. But nevertheless, we managed to get together and realize this particular resource that fortunately is being extended for the next 3 years, as you just heard. It was a major effort, and we are very happy that it's going to happen. And to help also for future research, after the doors were opened, we now have DigiMed Bayern Secure Cloud 2.0 for the next 3 years, and we hope that we will continue with the Bavarian Cloud for health research. And as you can see here, we also brought 2 ministries here of Bavaria together to work on this concept. But now going to the data, I mean, what did we do with this data lake? We wanted to identify individual signatures and work towards personalized treatment. I want to give a couple of examples in this respect. For example, genomics. We can predict the clinical risk to develop a stroke or myocardial infarction with clinical data. But we can refine this information by genomic data. And here's an example for this. For example, we can measure the risk by a clinical score called score 2, and people who live a healthy life have a low probability to develop heart attacks or stroke. They are most in the intermediate range and some are in the high range. If we now add genomic data to this, we can see irrespectively whether one is in a low, intermediate or high risk group, that genomics can multiply the risk that comes from clinical risk factors and thereby differentiate further the probability to develop a heart attack. And this can be used in populations to really refine individuals who are then at high risk and need more intensified treatment. And this we moved really to the ESC level, that's the European Society of Cardiology, in that we came up with a position paper that we said that genomic refinement of risk stratification makes more sense in the intermediate to high risk category. Here counseling with a polygenic risk score will help if it is requested to further differentiate risk and move quite a substantial number of people to a high risk category that needs more intensified treatment. Another example is proteomics. That is a collaborative work also with the Max Planck Institute. Here, very recently, Raphael Lermer won the global contest of identifying biomarkers of aging. This challenge was carried out all across the world, and he made first place with his biomarker prediction of aging in UK Biobank. I think it's a great achievement and a great example of the collaborative work in DigiMed Bayern. Another example of participatory work and multi-omics comes from Moritz von Scheidt, who worked on a chip that is a mutation that develops in a certain percentile of all of us during aging, but increases dramatically the risk for developing a heart attack or a stroke. Here you see that the survival rate is much lower in those who develop these mutations. Importantly, it will be to develop treatment options for these patients, and here are clinical studies already ongoing and being planned, and there's a big register now German-wide that has been initiated by Moritz von Scheidt, and the work that was possible through DigiMed, the German chip registry that will help patients with this rather common acquired mutation. Another big example of DigiMed Bayern, of course, is Froni. More than 500 pediatricians and close to 30,000 children were screened. More than 250 families with this mutation were identified. Guideline recommended treatment is being initiated, cascade screening in these families, and thereby a big step towards a better personalized and preventive treatment. Perhaps importantly, together with the German Society of Cardiology and the Deutsche Herzstiftung, we transported these ideas and concepts to the German Ministry of Health, and they developed a law, and that went through the cabinet for the prevention and treatment of heart and circulatory disorders. And a major part, actually the first chapter in this law, is to bring Froni concepts to the German situation. We hope that it will finally pass not only the cabinet but also the other steps in lawmaking, so that we will have the Froni concept at some point all across Germany. Another important example was also mentioned is the work that we did together again with the Deutsche Herzstiftung. First, to refine a test that allows to measure or estimate the risk of a heart attack. This test that has been developed by Fabian Starnecker and colleagues has like 30,000 clicks a month. So it is the most widely used test to estimate coronary risk in Germany, and beyond that the team developed the HerzFit app, which is, as we just heard, the most frequently used app in cardiovascular medicine in Germany. It's we see it as a personalized companion to estimate health risk and to also develop or learn about options to improve health. But not only it helps the individual patient, it is participatory, because we want to use the information that is generated by the hundred thousands of users of the HerzFit app to create a study database to learn about the trends in healthcare, and perhaps also identify groups within the society that may be of special interest for research questions. So I think another very promising tool for the future. So finally, a word on the data from the German health insurances, AOK Bayern and others, who generated offered data to us. By now it's about more than 3 million. It will increase to more than 10 million rather soon, and that will allow, with a long-term follow-up, to make predictions on risk. For example, here is the age distribution of these many people. We can recreate clinical studies that have been conducted or cannot be conducted for certain reason within this database. Here, for example, to estimate the risk of myocardial infarction, stroke or death by treatment in patients who suffered from acute coronary syndrome. So using these many data from the AOK, we basically redid the study that was initially formed on a rather small group of patients in acute coronary syndromes, and we basically recapitulated the same findings and reassured that the data from the randomized controlled trial is also relevant for the population. A final example here, which is heavily discussed in society, is the implication of global warming and coronary risk. And surprisingly, when you see here the temperatures and the number of acute coronary syndromes in the population, then only a small percentage is actually occurring at high temperatures. And for the epidemiologists, it's known for a long time that actually the cold period of the year is coming with a higher risk. That is an opposite what is being communicated actually in the public, but it is nevertheless only half of the truth, because I think here's a very interesting observation coming from the same data, that a sudden temperature rise increases the admissions for acute coronary syndromes, and not only acute coronary syndromes, but also mortality. So it is not a hot temperature, but it's the fluctuations in temperatures, and particularly the sudden rise in temperature, that creates risk. And obviously the risk increase is quite substantial. And it's not only for the first day after the increase of risk, but that lingers on for a number of days. Up to 4 days, there's a highly significant increase in risk after a temperature rise. So with this, I want to conclude that technological, ethical, legal, and social challenges of P4 medicine have been addressed in DigiMed. Comprehensive multi-omics data sets for personalized, preventive, predictive, and participatory medicine have been generated. Research and public tools for atherosclerosis have been generated. German laws for prevention have been inspired, which I think is quite an interesting achievement, and insights and structures have been created within the health system. In particular, an exemplary and transferable integrated digital health infrastructure for data storage, the Bavarian Cloud for Health Research. All this is possible because it was inspired, as I said, by Professor Domdai and managed by Dr. Jens Wieler throughout the years. I'm very thankful to both of you. I guess the success of DigiMed Bayern is to a large extent also your success. Of course, we want to thank the Bavarian State Ministry of Healthcare who supported DigiMed and the many teams that work together. Here are some names mentioned. I think it was a wonderful team effort, and I'm really proud that I was part of it. And with this, I want to thank you for your attention this morning. Thank you.
Dear Professor Schunkert, thank you very much for sharing the scientific and medical resume of the DigiMed Bayern project. Next comes Professor Daniel Rückert on the stage. And we are looking forward to your keynote, Daniel, for AI in medicine and the future. Daniel is Alexander von Humboldt Professor for AI in Medicine and Healthcare at the TUM University Hospital, where he is also director of the Institute for AI in Informatics and Medicine, and you are a professor of Visual Information Processing at the Department of Computing at the Imperial College London, among others. You have many professions, and we are looking forward to listening to you.
Thank you very much. It's a great pleasure to be here. Thank you very much for the invitation. And it's also very exciting to see a project like DigiMed because I think a lot of the potential of AI in medicine really relies on work as it's done in the DigiMed project. So let me start off by showing you 2 pictures at the beginning, which I think have sort of captured the imagination of a lot of people, because you see here the Nobel Prize winners for this year's Nobel Prize in physics as well as in chemistry. And one of the notable things for these gentlemen on these pictures is that a lot of them have sort of pioneered the field of AI and developed AI approaches, which have then sort of started to transform, for example, the field of chemistry. And I think the same is possible also in medicine. And I think I'm pretty sure over the next 10, 20 years, we'll probably see a similar development in medicine, and hopefully also not only scientifically, but also for the benefit of patients. So I think everybody talks about AI. I think last week's issue of the Spiegel, for example, had this cover page. And I think most of the doctors which I see in this room are not yet completely robotized. So that's also very good to see. But there's also a lot of hype. And if you, for example, look at something which came out just at the height of the pandemic, it also illustrates a bit that we have to be a bit careful how we communicate about AI and what are the expectations of what AI can actually do in medicine. Because, of course, in this particular case, in the COVID pandemic, AI has promised a lot. I don't know, some of you might remember that people said, oh, well, the AI can recognize your voice, whether you have COVID, whether you're coughing, how you walk. All of that hasn't really worked. And of course, good old-fashioned bioengineering and medical engineering has sort of helped quite a lot and sort of combat the pandemic. Nevertheless, I want to briefly sort of highlight what I think the vision for AI in medicine should be. And of course, it's very similar to what's done in DigiMed Bayern, because you think we need to take a lot of different data types, like from imaging, MRI imaging, for example, from sensors such as ECG. We need to combine that with clinical records, with omics, as well as with information about the lifestyle. And then we can sort of integrate all that information. And I think that was very nicely illustrated before. We need to overcome the silos in which these data sets reside and integrate them, for example, using an AI model. And that AI model then, of course, can be used to make diagnostic recommendations, but that's actually not really what we want to do as the endpoint. We also want to make predictions about how we should treat the patients and what the outcome of that treatment might be. So it's very important that we don't stop at, for example, just the diagnosis point or, for example, the risk stratification point. But of course, the other thing which was also illustrated and which is one of the aims of DigiMed Bayern is we want to identify the population, high-risk parts of the population, low-risk parts of the population. But again, I would argue we don't really want to stop there. We want to actually completely personalize the risk prediction. And again, I think it's very nice to see that being done in the DigiMed project. And of course, that's also something which I also wanted to highlight, that there's of course a lot of potential in using AI to make predictions about, for example, certain drugs, how they behave, toxicity. For example, this is a very nice paper which recently came out in Nature Medicine, where the authors used these type of AI methods, neural networks, as a sort of way of integrating information from different diseases and medication in order to, for example, predict the likelihood of contraindication or the likelihood of indication. So there's a lot of potential here. There are many other tasks, and I've just listed some of them. Some of them are quite sort of mundane, but they still have a very significant impact, for example, when they can actually free up doctors' time to actually look at treating patients rather than doing paperwork. So I want to show you one quick example of AI in a cardiovascular domain. I've chosen an imaging domain because there's a lot of AI solutions which are out there which are actually deployed in radiology. And the entire radiology workflow is, of course, a sort of pyramid which sort of starts with image acquisition and ends with diagnosis and prediction. But one of the things you can do, and I just pick here the example at the bottom of this pyramid, is, for example, improving how you get actually data about a patient with cardiovascular disease. So if you sort of think about this, if you do, for example, an MRI scan of a patient, you collect data from that patient. You want to be as fast as possible to collect that data so the patient doesn't have to lie in the scanner for a very long time. And in addition, the patient typically has to hold their breath during the acquisition. And what you typically do is you reduce the scan time, you play a few tricks, but you also then get very poor data, like what you see, for example, on the left-hand side. So if I accelerate the imaging very much, so that the patient, for example, has to only do a very short breath hold, like 2 or 3 seconds, I get images which look like on the left-hand side. Now, I'm pretty sure that none of you would be able to diagnose a patient based on images like this. We typically want to acquire images like on the right-hand side. But for that, the patient has to do a breath hold of around 12 seconds. So that's, for most of you, no problem. But if you have cardiovascular diseases present, that might be a problem. So with the AI, we can actually generate the images which look like the ones in the middle column, and we use the data which is on the left-hand side to actually generate these images. And that means we have diagnostically interpretable images, but now acquired very, very fast, and therefore we can use them in a clinical context much more reliably. Now, MRI is just one imaging technique. We can, of course, also do this with brains, and I wanted to highlight something which is a problem. Unfortunately, I didn't have an example here with a cardiovascular example, but it's very important that you use the right data to train your AI algorithm. So if I want to do the same thing I showed you on the previous slide with brains, you can see this here. If I train with brain MRIs, I get very nice reconstructions. If I now use the wrong type of data to train, for example, an MRI image of a knee, to train my algorithms, then for some low acceleration factors like you see at the top, you still get an image which looks like a brain and looks actually very close to the reference. But at the bottom case, you suddenly start to see something which looks a bit odd. And if you have ever seen an MRI of a knee, it looks like it's a knee appearing inside the brain. And that's where the AI starts to hallucinate, because it doesn't have the right data. And that's why, for example, curating large data sets is so important and so useful. Just wanted to highlight one other thing, which is a result of this, which is very interesting. Sorry that this image here looks a bit blurry on this slide. But for example, you can use these technologies to make imaging much more accessible. So this is a science paper from earlier this year, where people started to build very low field MRI scanners. So typically MRI scanners require very, very strong magnetic field, way stronger than the Earth magnetic field. That makes them very expensive to run. You need a lot of cooling and so on. These people have developed a very low field MRI scanner, 100 times lower field than what's conventionally used, meaning that these MRI scanners are way cheaper, around $20,000 to $50,000. They can be built almost by yourself, and they're of course much more deployable all across the world. And they produce very nice looking images. Actually, these images are blurry because I think the PowerPoint version on this PC is slightly different. It's not because this is a low field MR scanner. So if you check out the original paper, they look very nice. And you can apply the same concept, for example, for ultrasound. Use very cheap sensors, which you can then connect with, for example, handheld devices, or you can use this to reduce radiation dose in CT. So this has a lot of application. I also wanted to very briefly highlight some of the challenges, and this is where I think DigiMed also comes in, because I think you will see that a lot of these challenges have to do something with the data. And if you look at sort of, again, a concept of DigiMed, that we want to have trustworthy approaches in medicine, then you see what, for example, the European Union would define as trustworthy AI, these are all components of trustworthy AI. Many of them sort of perhaps outside my remit of what I sort of work on, but I wanted to just highlight those 4 which are here in red, because they are the ones which perhaps also very strongly relate to some of the technical concepts in DigiMed. And the first one is an issue of bias and fairness. So if I build an AI model to predict the health of a population which looks like this, then of course that model is probably not really appropriate for the population on the right-hand side. And the real population, of course, looks much more like the one on the right-hand side. This has also been very nicely illustrated in a paper by Ziad Obermeier, where he showed that actually, for example, for cardiovascular risk, these sort of biases make it even into healthcare policy. So this is not something which is only due to AI, but actually is sort of has been something which has been around in medicine for many years. The other thing is, of course, human population is incredibly variable in terms of what we have. We typically use data which was already illustrated like in UK Biobank, and this is sort of, for me, UK Biobank looks like this population of pumpkins. But of course, if you only use that type of population for AI modeling, then this will not particularly work if you, for example, have a very clinical population where you have much more pathology and therefore much more variability as a result of these sort of pathologies. And finally, of course, you can also have lots of variation which is simply due to how you measure things. In the imaging sense, what field strength you use, what sequences you use, what modalities you use. And all of this, why I'm telling you all of this, because all of this comes down to how much data you have to train your AI algorithms. And this is something which is very much related to what was discussed earlier. There's a headline from a UK newspaper where somebody argued a couple of months ago that actually it's important for researchers in the medical field to have access to all healthcare data, for example, of the UK system, the NHS, of course, which is much more centralized than the German system, but that actually really to make advances, you need to have that data access and you need to build these data infrastructures, which, for example, DigiMed is building and which will hopefully continue in the Bavarian Cloud for Health Research. Of course, one of the things which is also then often discussed is how do we make sure that we also ensure privacy, because of course patients have a right for privacy. But I wanted to just argue that there are lots of technical solutions which are now emerging, which range from trusted research environments to, for example, privacy-preserving machine learning approaches. So all of this can be tackled, and I think it has to be tackled from a technical point of view, from a legal point of view, but also from an ethical point of view. So I want to finish by just highlighting, I think, what I think also are the very exciting opportunities for which are coming up and which I think will hopefully also shape the future of cardiovascular medicine and AI research in that domain. And that is based on 3 trends which I think I currently see. So the first one is people, so this is more technical, but for those of you who are interested in this, people have switched from traditional neural networks, which are actually the ones for which Hinton and Hopfield got the Nobel Prize in Physics, to a specific version of neural networks, which are, for example, very prominent in language processing, which ChatGPT uses, and these type of approaches. And these are called transformers, and they're very powerful because they sort of learn very long distance relationship in your data. The second thing is we always thought we need perfectly annotated data for training our AI algorithms. And that would be very nice if we have it, but we realize in many scenarios, in particular in medicine, we'll never have perfectly annotated data from millions of patients. So people have developed in natural language processing, again, the ideas of this self-supervised learning, where, for example, you take some text, you black out certain parts of the text and you try to reconstruct the text, and that actually helps the neural networks to learn semantic meaning of what is in the data. And it works surprisingly well, as you probably all know from using ChatGPT. So this also has a lot of potential, I think, in medicine. And finally, of course, we can use these foundation models, large language models, which are now sort of models which are trained on huge data sets, but then they can solve a lot of different tasks. So they're not only that AI model which is just developed for that one task, but you can actually use this for a number of different tasks. And I think that's also something we want to give to clinical colleagues, because quite often you want to then sort of ask another question after you've got one answer. For example, why do you think this is a case, and so on. So there are lots of potential applications of these large language models which combine these three ideas on the previous slide. Of course, we can use them for question answering, for image classification, for genomic variant calling, and lots of different applications. But I think something which is also very important is they can also help a lot with communication. And there are now the first studies which come out which say actually that some patients prefer talking to chatbots which are driven by large language models because they show more empathy than perhaps a clinician will show. And of course they can be customized to the preferences of individual patients. And of course also in education these models play a huge role. I just wanted to also highlight, this is a paper from some colleagues of mine here in our group who sort of looked at how good are the current models. Can we actually already start using them, deploying them in clinical practice? And the solution, the short answer to that is no, you can't. They really have a lot of shortcomings, but they also have a lot of potential. Some of the shortcomings are, for example, that they are sensitive to the order in which you present information to the language model. So if I say to the language model the patient has high blood pressure and is diabetic, I get a different solution to if I say to the language model the patient is diabetic and has high blood pressure. So of course that's not very logical to a human, but it shows some of the shortcomings which are out there. Nevertheless, I think there's a lot of potential in this. And with this, I wanted to stop here and just highlight before I I wanted to thank of course, all the colleagues who have sort of worked on this. But I also wanted to make a sort of plea that you sort of take whatever you have developed in DigiMed, and in particular the data infrastructure, which I think serves as a very nice blueprint for how things can work in a space where we need to move medical data into a secure environment so that it becomes available for research, whether it's AI research or whether it's medical research. I think that needs to really go forward, and I'm very grateful that you have developed this, and I think it sets a very nice blueprint for the future. Thank you very much for your attention.
Daniel, this helped a lot to understand better where AI in medicine goes. Thank you very much. And I think we have time for a few questions to the presenters. So do we have a mic or just speak loudly, perhaps?
So I have a question for you. Wonderful talk. Thank you so much. You worked in England for quite some time and now in Germany. So what is the difference between the two cultures so that England has so wonderful resources, not only UK Biobank, but there are many more, and we are lagging behind?
So I think one big difference, as I see it, is that there are fewer stakeholders in the system in the UK, especially on the healthcare provisioning side, because there's no interplay between insurers, between private practices, hospitals, because they're all sort of one system, the NHS. And that, I think, makes it much easier to do top-down, implement some of these ideas, which I think the ideas are also there in the German system, but it seems much more complicated because you need to get many more people to agree that this is a good idea, and perhaps it's also something which you have sort of noticed in the DigiMed project. You have a lot of partners, and I don't know, perhaps you can say something on how difficult or how easy it was to bring all these partners, from healthcare providers to insurers to patient representatives all together.
Well, I can tell you about many sleepless nights in this respect, but I guess it takes a long breath I mean, with the obstacles that you just mentioned within the German system, to, convince the lawmakers and all the players in the system that this is the way to go, and not only to rely on data that is coming from other places like the UK. I guess communication is the tool in this respect. Fortunately, we had very open ears within the Bavarian ministries, also in the federal ministry. So I had a chance to visit Professor Lauterbach and tell him about the Froni project, and he was very interested and really took it as a blueprint also within his house. But this sort of communication really needs to take place, and then obviously players within these ministries that say, okay, we need to do this, and we have to set the rules that it's possible to do. Quite a challenge, but communication, I guess, will be the key.
Thank you very much. Any questions from the audience?
So thank you very much for these very interesting insights. One question that was on my mind is, how do the infrastructures that you build in DigiMed relate to other infrastructure projects in Germany? So in particular, could you disentangle a bit what of the medical informatics infrastructure you're using, how you're building maybe on top of this? You mentioned it, but maybe you could explain it a little bit more.
Yes, perhaps I can answer first. Perhaps you have some different view or additional view. So the data integration center which has been built at the German Heart Center was built according to the standards and procedures of the Medical Informatics Initiative in Germany. So that, I think, is key, and data standards which are changing, of course, over time and developing, have been considered. The cloud at the Leibniz Supercomputing Center, frankly, I'm not so technical. There have been own developments, I think, which also raise interest of the big industry players like Google and Amazon, which is quite remarkable. At least I have been told, which is quite remarkable, because this is a relatively small team with small resources. So I cannot answer more to that.
More question? Du hast noch eine Frage?
Thank you, Professor Rückert, for that wonderful talk. I was also going to ask a question on the infrastructure that are built within DigiMed also. What I was wondering is, from a technical point of view and from your scientific point of view, is there also a justified need for an own Bavarian cloud and an own Bavarian trusted research environment? And why can't that be just used on or practiced on commercial solutions that are used by the UK Biobank, for example? Why do we have to build that from a scientific point of view? Because, the legal and ethical considerations have been made clear. Is that also a scientific perspective to that?
Okay, that's a very relevant question, kind of expected and more frequently asked. First, why don't we stick to a commercial solution? We have qualified this at the beginning when we started the project in 2018 and prepared it. As I told, we recognized we need something like this, and of course we considered also fully commercial solutions like AWS or Google or Microsoft. But this was not politically supported very clearly. So this alone was a showstopper. And now I tell you also my personal belief is there are reports which are also by the federal government expert reports about the situation, in economic situation in Germany. And with regards to cloud technologies, I recently read a very large report which says that Germany is to 100% dependent, to 100% on non-European cloud technology providers. And I think this is not a healthy situation, such a dependency. And I think the public must at least have a hand into this and have some control. And another argument why you, in addition, I'm coming from industry, so I'm very much for using industrial suppliers. But first, you need to be able to keep the control on what you do, have no dependencies. You also have the problem that you dig a hole when you stick to one provider. Okay.
Perhaps one word to the Bavarian genome database.
Bavarian Cloud for Health Research. Okay, why do we need this? We simply need such a TRE as a service.
The genome. I mean, they were asked by the public to be on a federal run cloud solution.
Yes, that's the Genome Research Center of the Modellform Genomsequenzierung. This was given by politics, as I said before. It had to be 100% public, so no chance to.
Just two very quick points. First of all, I think academics are generally poor. And for example, UK Biobank has now switched their model completely to only cloud computing. You can no longer download UK Biobank data. And some of our colleagues, for example, looked at some of the analysis which AI people have done. A single run of that analysis costs on the UK Biobank platform £50,000. So that makes a lot of research no longer viable, no longer, you cannot pay for that unless you have your own sort of, the Leibniz Rechenzentrum, for example, has its own infrastructure, and we as academics don't really pay because it's sort of government subsidized. But of course, in principle, you could probably, from a technical point of view, that you could do it. The second point I want to just make is, I think DigiMed, for example, started very locally, sort of Munich sort of centric approach. And the Bavarian Health Cloud will make it a bigger into a Bavarian one. Your question, why don't you use a bigger one like European Health Data Space, is I think my experience in all these initiatives is if they don't start from the ground up and they start small, these big picture visions, I think the Medical Informatics Initiative, for example, has not delivered as much as people have hoped, because it sort of was this huge idea and let's start with a big idea, but don't really think about how we build it. And I think here is the opposite, sort of you start very locally and you have a good idea and then you build it up. But the idea, for example, of the Bavarian Health Cloud is in no means to sort of build a border around sort of the Bavarian sort of data, but instead simply say, actually, we have to get started. Somebody has to actually build a working version. And then if we, for example, already talked to Baden-Württemberg about they have a similar idea, we combine them. It's not the idea to build a lot of island solutions, but you have to start somewhere. That would be my answer.
Very good.
Yeah, thank you very much. We need to stop this discussion. We went also into the next point and on the agenda topic. And we wanted to have a patient here reporting from the German Heart Center, reporting about his experience with DigiMed and the associated treatment. But this patient became ill yesterday, had fever, and Moritz von Scheidt, Dr. Moritz von Scheidt, cardiologist at the German Heart Center and a key researcher, took over. I think last night you worked a little bit to make the presentation of the patient. Thank you very much.
Yes, thank you very much. Good morning. So it's my pleasure to provide the patient's perspective. In my eyes, this is very essential, as the overall aim is to improve patients' care. So I would like to point out the P4 medicine principles and provide the insights of a patient. You can see his name, Oliver Putzer. He's a very nice and interesting person. I'll provide you some information. So to start with, why is it relevant what we do? It was pointed out cardiovascular disease kills around 19 million people worldwide each year. And the acute scenarios like myocardial infarction and stroke account for 85% of these cases. And most interestingly, you can see that around 2/3 of these acute events could have been prevented if these patients would be treated by optimal risk factor management. So this is impressive. This is something we can't reach with any medication so far. So I would like to provide the example, and this is Oliver Putzer, so he can't be here today, but his perspective on what we are doing is important for our daily business. So it was introduced, the P4 medicine, as being predictive, preventive, personalized, and participatory. I think for the 3 upper ones, we are quite good. But how to engage and motivate our patients on a long-term journey to keep track of their risk factors. So, an insight on his medical history. In October 2023, when I contacted him, he was 50 years old, slightly overweight with a BMI of 27. He suffered from a prior myocardial infarction in May 2021, received 2 drug-eluting stents. He has a normal left ventricular ejection fraction, so he was lucky. He came to the hospital within 30 minutes after acute chest pain. He has quite some risk factors: arterial hypertension, hypercholesterolemia. He is an active smoker, half a package a day, so sums up to around 15 pack years in this patient. His 24-hour blood pressure was elevated. The LDL cholesterol was out of any leak, so he did not tolerate well atorvastatin 40 milligrams in the beginning, so he was brought to 10 milligrams and no one cared afterwards, and he is slightly in a pre-diabetic state. So I'd like to show you the angiogram of his myocardial infarction. May I ask the technical team to start the left video by clicking with the mouse into the, exactly. Thank you very much. So you can see an acute occlusion of the mid-right coronary artery. So it's a plaque rupture with thrombotic overlay. So the blood flow is basically stopped in the mid-RCA. And if you go to the right video, you can see after the implantation of 2 drug-eluting stents that the blood flow is fully recovered. Thank you very much. So what did the patient do? Luckily, he consented in our biobanking agreement. So he donated blood for DNA sequencing and provided his clinical data for cardiovascular research. And within the DigiMed environment, we performed deep DNA sequencing. And we identified an acquired somatic mutation risk factor, clonal hematopoiesis of indeterminate potential, short CHIP. And this acquired mutation is a novel and very relevant cardiovascular risk factor. In his case, it's a loss of function mutation of the TET2 gene with a very high mutation load. So 46% of his leukocytes are affected by this mutation. So I called out of the blue the patient after 2 years having his blood sample in our biobank and asked him if he would be interested to learn something about CHIP. And he said yes. So he came by, and I learned something about his personal history. So he has a stressful job. He's a head of the logistics management for 2 symphonic orchestras in Germany. So basically he described his work as intense with very stressful moments. So customs in Asia are kind of the most stressful situations he experienced. So he's managing around 240 instruments with a net worth of over 30 million euro. That's more than we received for the DigiMed project. And average 4 months of a year he's abroad, living in hotels all across the world. His social life, he's married, he has a 1 adult daughter. He's expecting his first grandchild early next year. He enjoys music and reading and the resources that he comes with. So he's a motivated one. He wants to learn something about his medical conditions, and the key goals he had is to reduce the stress burden. He struggles with motivation for lifestyle changes, so he knows that smoking, of course, is harmful, but he never stopped. He has no idea of his long-term risk, so at the end of our first session, he felt not adequately informed regarding how risk management could work in his case. So he is interested in understanding and managing his personal risk. He is interested in using electronic devices and health systems. And he likes competitions. So he likes to have a goal and work hard for this goal and reaching it over time. So we invited him as the very first patient to the German CHIP registry, which is a non-profit. It's thought to inform patients and also scientists and medical doctors for this novel risk factor. It provides longitudinal follow-up of these patients, and it's including a managed care program. So he was the first one that received access here, so he was one of our beta testers. I do not know where this lower part comes from, so should not be in the presentation. Nevertheless, I think what I can point out, so we know everything about this patient, and he's basically asked to update that annually. He's seen annually in our outpatients clinic and with the hematologists. And what was most relevant for him is to understand his 10-year risk, and we used a visualization here. And what is interesting is, so 38% 10-year risk for myocardial infarction, stroke, and cardiovascular death. That's criminal. That's super high. And 18% derive from his classical cardiovascular risk factors. This comes from his CHIP mutation, so from this acquired mutation. And this would be his risk, so it can be lowered to 31% if he stops smoking, has optimal control of his cholesterol levels and hypertension. The other part is that a CHIP also affects his hematological risk. I won't go into much detail, so the risk to develop a novel neoplasia, myeloid leukemia is between 0.5 to 1% per year, so it's on the lower side. So as a cardiologist, I focus most on the cardiovasculars. Nevertheless, we have the hematologists on board to treat these patients together. After the visualization and giving him the message that it's important that he has to optimize his risk factors, he stopped smoking, and he's still a non-smoker. He reduced 5 kilograms of body weight, so he has now a BMI of 26, and the pre-diabetic state was relieved. We brought him on rosuvastatin and ezetimibe, bringing into the guideline recommendation for LDL cholesterol levels, and we improved the anti-hypertension medication. So regarding the active participation and the motivation for the patient, because I think that's the most critical and also the most difficult part. In his case, this loss of function mutation is connected to a strong upregulation of a pro-inflammatory cascade. It's called the NLRP3 inflammasome, with caspase-1 as the central enzyme, cleaving the pro-form of the interleukin-1 beta and interleukin-18 to the active forms. And this is interesting because we have now antibodies ready against these targets. And this is super interesting because we have Mike Mendelsohn in our DigiMed Consortium Symposium today, and what he is the head of a phase 2 trial. So this is the very first anti-inflammatory trial in patients with this CHIP risk factor, and what is tried is to have the combined antibody against these both candidates. This is a phase 2 trial, so it's only 12 weeks, and it's only measured with surrogate outcomes, so like the improvement regarding the pro-inflammatory cascades. But the most important question and the long-term question that's driving us and driving the guidelines is, does TET2 CHIP mutation carriers profit from anti-inflammatory therapy on the long term? I have a clear answer to that. In my opinion, of course, yes. To sum this up, what are the key messages that were learned from Oliver Putzer? So he stated, make health insights simple to understand and actionable. Use my data to personalize my care. Engage me in my health journey and make me an expert of my health. And this needs time. So you have invest time in helping the patients understand their conditions, provide tools that motivate me over time, keep me a non-smoker, use my data to also improve the society, improve care in general, and inform me about clinical trials. So this is specific because he has a risk factor that drives his disease. And I'd like to end with a quote of him: "I'm deeply grateful for the past 12 months of support, care, and opportunities. Please keep up the great work." So from the patient's perspective, I think it's essential, and they like what we do, and we should empower these patients in the future too. Thank you very much for your attention.
Thanks, Moritz. I'm sure the patient would have demonstrated this from a different perspective, less scientific. Thank you very much for that insights. And we now go into the coffee break. Two housekeeping topics. First, we have to be really in time. 10:40 we come back. And secondly, please don't smoke in the entrance area of the building. That's it. Yes.